This visualization shows how we typically perceive modern data networks as an invisible, magical, and infinitely scalable cloud. In reality, every email you send, every video you stream, and every file you transfer relies on highly rigid, physical hardware. A computer network is a collection of interconnected devices designed to exchange data and share resources. To understand the internet, we have to look past the abstraction of the cloud and examine the exact physical infrastructure and logical rule sets that govern data. We will understand modern networking by building a functional network from absolute scratch. We'll introduce new hardware only when we hit an engineering bottleneck that demands a specialized solution. This diagram shows our starting point, a stark blank canvas containing two completely isolated computer nodes. Scaling this void from two disconnected machines into a global, fault-tolerant system is a matter of solving sequential logistical problems. These two isolated endpoints are nodes, the physical devices, like computers, printers, or servers, that need to send or receive information. To communicate, these nodes require a physical connection, known as transmission media. This includes wired links, like Ethernet or optical fiber, and wireless links, like radio signals. Once connected, we face our first bottleneck. Sending large monolithic files across a single wire clogs the connection and blocks other traffic. We solve this by breaking data into packets, small, manageable chunks that travel efficiently across the line. Because these packets arrive in pieces, both nodes must follow strict, predefined rules to ensure the data is formatted, transmitted, and reassembled accurately. We call these rules protocols. To guarantee these packets reach the correct destination, each device is assigned a unique numerical identifier called an IP address. Physical wires become useful when data is broken into packets, governed by protocols, and properly addressed. The next bottleneck arises when we connect multiple nodes. Wiring every machine directly to every other machine creates a geometric nightmare of cables. This diagram shows the simplest solution, a central connection device called a hub that links multiple nodes together. However, the hub lacks intelligent routing. It blindly broadcasts any incoming data to every single connected device simultaneously. This method is highly inefficient. Nodes are forced to process packets meant for others, which consumes available bandwidth with useless traffic. It also introduces a security risk, as sensitive data packets are delivered to unintended recipients on the network. To fix this, we replace the hub with a more sophisticated device, the switch. The switch manages internal data communication by reading the packet's destination and sending it exclusively to the intended device. Intelligent, targeted routing at the center of the network prevents the gridlock that occurs as local clusters grow. Another bottleneck appears when connecting entirely separate local networks. We link these segments using a bridge. The bridge filters traffic by checking hardware addresses. It keeps internal traffic contained, only allowing packets to cross if they belong on the other side. Bridges work for connecting two segments, but they cannot navigate the massive web of countless interconnected networks that make up the internet. To connect local networks to the broader outside world, we introduce a router. Routers analyze IP addresses to determine the best path for forwarding data packets across complex external networks. This establishes a clear division of labor. Switches manage internal local traffic, while routers handle navigation to the outside world. This brings us to the network edge, the perimeter where our controlled local network interfaces with the external internet. Data leaving our router requires physical and logical translation to survive the transition. A modem converts our internal digital data into signals suitable for transmission over the internet service provider's external lines. Next, we use a gateway. The gateway translates data between dissimilar network systems that use different protocols, ensuring they can communicate. Finally, we place a critical security device at the edge, the firewall. The firewall acts as a security checkpoint. It monitors traffic and blocks unauthorized access based on defined rules. Moving between networks requires this dedicated hardware to translate the language, alter the signal, and enforce security. Modern nodes are often wireless, which requires the addition of access points. Access points extend the wired network into a wireless Wi-Fi coverage area for mobile devices. With the physical infrastructure established, we must define the logical governance of the network. In a client-server architecture, a central server node dictates behavior and manages resources for subordinate client nodes. In a peer-to-peer architecture, there is no central authority. Every device operates equally as both a client and a server. Hardware determines how data moves, but the network architecture determines which machines control the flow. This schematic shows our fully built model, where packets navigate a gauntlet of access points, switches, firewalls, routers, and modems. This infrastructure enables efficient resource sharing, reliable data access, and the ability to scale as demand increases. The global internet consists of millions of these individual local architectures, all interconnected through the same fundamental routing logic. Understanding a network means recognizing the global aggregation of specialized physical hardware, precisely engineered to solve sequential logistical problems.